Dark matter. More than a quarter of the universe is made of something we cannot see and have never directly detected. We know it exists because galaxies spin too fast. The stars at the outer edges of spiral galaxies move at roughly the same speed as the stars near the center. In a galaxy made only of visible matter, the outer stars would fly off into space long before they could reach that speed. Something invisible is holding them in. The same invisible substance is bending light, more than visible mass can explain, and shaping the large-scale structure of the universe. Every experiment designed to find it, underground, in orbit, and in particle accelerators, has returned empty. What it is remains completely unknown. Dark energy. The universe is not only expanding, it is expanding faster and faster. In 1998, two independent teams measuring distant exploding stars expected to find that gravity was gradually slowing the expansion down. Both teams found the opposite. The universe is accelerating outward. Something is pushing everything apart with increasing force. Physicists call it dark energy, and it makes up roughly 68% of everything in the universe. The leading idea is that empty space itself carries energy, a kind of outward pressure built into the fabric of the universe. No one knows what that pressure is, why it has the value it has, or whether it will keep increasing forever. Matter-Antimatter Asymmetry. Every particle has an opposite version, called an antiparticle, with the same mass but opposite charge. When a particle and its antiparticle meet, both are destroyed instantly and converted to pure energy. The Big Bang should have produced equal amounts of both. If it did, they would have destroyed each other completely within the first second, leaving nothing but light. We exist, which means something produced slightly more matter than antimatter in the earliest moments. The excess survived. We are made of it. The process that caused the imbalance has never been identified. Arrow of time. The laws of physics work identically in both directions of time. A film of two billiard balls colliding looks perfectly valid played forward or backward. Yet we only ever experience time moving in one direction. The past is fixed and the future is open. A cup falls and shatters. It never reassembles. The accepted explanation is that the universe began in an extremely orderly state, and disorder has been increasing ever since. That direction of increasing disorder is what we experience as forward. But this only pushes the question back. Why did the universe begin so orderly in the first place? That remains unanswered. Black hole information paradox. Stephen Hawking showed in 1974 that black holes slowly lose mass by leaking radiation and eventually disappear completely. The radiation they emit is featureless. It carries no record of what fell in. A black hole that swallowed a library and one that swallowed a cloud of hydrogen gas would produce identical radiation on the way out. But one of the deepest principles of quantum physics says information can never be permanently destroyed. The total amount of information in the universe must be conserved. If a black hole vanishes and its contents leave no trace, something has been permanently erased. Whether that is possible, and what it would mean for our understanding of reality, is unresolved. Quantum measurement problem. A particle does not have a definite position, speed, or spin until something measures it. Before measurement, it exists in a blurred mix of all possible states at once. The moment it is measured, it snaps to a single definite value. Quantum mechanics predicts the odds of each outcome with extraordinary accuracy. It gives no explanation for why the snap happens, what counts as a measurement, or whether the other possibilities simply vanish or continue somewhere. Some physicists say every outcome occurs, and the universe splits into separate branches with each measurement. Others say the question is meaningless, and the math is all there is. No version of this answer has been tested. None has been ruled out. Quantum gravity. General relativity describes gravity as the bending of space and time caused by mass. Quantum mechanics describes every other force through particles and probability. Both theories are among the most precisely tested ideas in all of science. Neither accounts for the other. Near the center of a black hole or in the first instant after the Big Bang, both are needed at once. When physicists try to apply quantum methods to gravity, the calculations break down and produce infinite answers that mean nothing. no one has found a way to combine the two theories into one that works. String theory is the most widely known attempt. It has not yet produced a prediction that any experiment can test. Neutrino mass. Neutrinos are among the most common particles in the universe. Billions of them pass through your body every second without interacting with anything. For decades, physicists assumed they had no mass. Then in 1998, an experiment in Japan observed neutrinos changing from one type to another mid-flight. That change is only possible if different types have slightly different masses, but the framework that describes all known particles was built on the assumption that neutrinos are massless. It has no explanation for where their mass comes from. The exact values of the masses are still unknown. Whether a neutrino is its own antiparticle is also unknown. The answer to that second question may be directly connected to why matter dominated antimatter in the early universe. Hierarchy problem. Gravity is almost unimaginably weaker than the other forces of nature. A small magnet can lift a paper clip against the entire gravitational pull of the Earth. At the level of individual particles, gravity is roughly 10 trillion times weaker than electromagnetism. This gap is strange enough on its own. The deeper problem is that physics has no natural explanation for why the gap is so large. A particle called the Higgs boson, which gives other particles their mass, should be pulled toward an enormous mass by constant quantum activity in the vacuum. To match the small mass actually observed, two huge numbers must cancel each other to more than 15 decimal places. A cancellation that precise does not happen by accident. Something is holding the Higgs mass down. No one knows what. Cosmological constant problem. Quantum mechanics says empty space is not truly empty. Pairs of particles constantly flicker in and out of existence in the vacuum, giving it energy. This energy should act like a pressure pushing the universe apart, which is exactly what dark energy does. So physicists have a way to calculate what dark energy should be from first principles. The result is wrong by a factor of at least 10 followed by 60 zeros. Some calculations put the discrepancy at 10 followed by 120 zeros. That is the largest gap between a theoretical prediction and a measured value in the history of science. Something is almost completely canceling the vacuum energy, leaving only a tiny trace. What is doing the canceling is entirely unknown. Thanks for watching. Which of these mysteries intrigues you the most? Let me know in the comments down below. Also, please remember to like and subscribe if you enjoyed this video.